Hi, Mick McQuaid here, welcoming you to the first of two videos for day 14 of iste780, Data-Driven Knowledge Discovery. And this video is on local regression, which is depicted here, and general additive models. And then the other video will be on our lab for this chapter, which includes these things plus all of the other nonlinear things that we've been looking at. So local regression is really interesting, and I think this is a really excellent representation of it. Let's take a look at the algorithm for local regression. We're going to gather a fraction of training points that are closest to x naught. So we have some point x naught. We're going to assign a weight to each point in the neighborhood so that the point farthest away has the weight 0 and the closest has the highest weight. All but these k nearest neighbors get weight 0. Fit a weighted least squares regression, and the fitted value at x naught is given by f of x naught, and then this simple model. So in this picture here, this is x naught and this is x naught for a span. I should mention what a span is. So a span is a fraction of the total observations, and it's the most important decision that you have to make when you're doing local regression is how big should the span be. In this case, I have to guess that the span is a third, that we have this span over here, this span here, and then one more span over here to the right. This is a simulated data set, and I'm just guessing that they've chosen the span to be 0.33. We'll look at some examples in a minute of a couple of other spans. And by the way, the smaller the span, the more flexible local regression is. The larger the span, the more interpretable local regression is. So the way that the local regression happens, this has had a bell curve superimposed on it in order to highlight the fact. I mean, this is just, there's no spatial reason to have this here. It's just to highlight the fact that we've chosen this point x naught, which is at the center of the span, and that's going to be the target for our local regression. This is the least squares line that's going to result from that local regression, and the bell curve indicates that these points nearby get the highest weight, and with a normal distribution, diminishing weights go to the points farther and farther and farther away until we get outside of this where everything is just 0. None of these points, none of the gray points have any weight at all. And the same thing is true here, and then the same thing is true presumably for a third span over here. So we get this model, which is represented, I think, by the orange. Yeah, this is a weighted linear regression fitted by this orange line segment, and that segment is made up of these. Now, let's just take a quick look at another example of local regression here. Yeah, so here it is. Here's local regression with two different spans, and it's done on the age-wage data. And you can see that just at a glance, you can see that the one with the smaller span is a lot more flexible. It's a much more wiggly, jumpy curve. And the one with the larger span, you can guess immediately, is more interpretable because it has a much smaller degrees of freedom. And we talked previously about how effective degrees of freedom don't exactly correspond to the number of free parameters. The formula for coming up with them means that they can be fractional. So anyway, that's about it for local regression. It is only typically used in low dimension. I think that's mentioned here. Yeah, here we go. So it suffers from the curse of dimensionality because in high dimensions, there aren't going to be very many nearest neighbors. Just the same problem that k nearest neighbors suffers from. So keep that in mind when you're choosing models. Okay, now let's talk about generalized additive models. So everything that we've been talking about in Chapter 7 so far could be construed as an extension of simple linear regression. This technique, generalized additive models, could be construed as an extension of multiple linear regression. And they're a more general framework. It's not the most general framework. Actually, in the next chapter, we're going to look at an even more general framework. But this is a more general framework than what we've been looking at. And the way that it's more general is that we have the freedom to choose a different function at each of these points. So each of these points can be, some function that we think is going to work well. And for example, with education in the wage data, that's a matter of levels. That's not continuous the way that these are. So we might want to handle it differently. So here's an example of handling. Let's see. So we have natural splines here and here, and then we have a step function here, and we get a very interpretable result. And I think we're going to look at a few more examples of this, and I think of the examples that we're going to look at, this is the best one for year because it seems, or at least intuitively, it seems to account for the crisis of 2008. If you recall, in 2008, the economy collapsed around the subprime mortgage crisis, and wages stagnated. And this is the only one of the ones that we're going to look at that captures that. I'm not so sure that this step function is so fantastic because I'm not convinced, intuitively, I'm not convinced that education has this kind of really very sharp influence on wages. But it could well be. Here it is with a different, so we have this exact same thing, but we have smoothing splines with 4 degrees of freedom here and 5 degrees of freedom here. You can see that we have somewhat different shapes. This is has a less pronounced dip at 2008. This is a smoother curve. This is still kind of out there as far as I'm concerned. Oh, and by the way, the education has been collapsed. They actually have more categories of education than this. I think education is coded in years, and they've collapsed this into 5 categories in this example. Now we can also do the same thing with qualitative data. I'm just going to skip that for a second. We'll come back to the pros and cons. We can also do this with qualitative data, and we can use the same example that we used earlier in the chapter with calculating the probability, or I should say modeling the probability of being in the high wage earners group. That's the greater than 250 group. And so here's a picture of that. And it's quite suspicious looking. This isn't terribly informative. This looks very similar to what we've seen in the quantitative models. Remember that although we have a qualitative predictor, the other models that we have just talked about were both quantitative response variables. And this is a qualitative response variable, the probability. So this is amounts to a classification problem, the probability that somebody's a member of one class or the other. This looks even more unconvincing than the sharp curve, and it turns out that the reason for it, and this is, I think, it is a good lesson. The reason for it is this category over here: people who have less than high school. There's no one in this category who earns more than 250. So consequently, this the presence of this category has a terrible dampening effect on everything else. So what they did for this later example, this is roughly the same thing, but they've taken I think in all of these they've removed all observations where education is less than high school, and I think this results in the best. What can I say? At least the most intuitive representation of what I expect to be the effect of education. The effect of education isn't as wild as it is in the previous two. So I think that this works out to be a more convincing model for education. Still not convincing for these. It's certainly not convincing for year. and similar for age, similar to the others for age. I mean, we get the same point that's raised for age, that wages tend to increase with age for a while and then dip. Okay, so, and that's about it for general additive models, except that I'd like to go over these pros and cons. So these are the pros and cons. Some of the pros are sort of versions of each other. So the fact that it allows us to give a nonlinear fit is good, because it's better than standard linear regression. Nonlinear fits can be more accurate. These are sort of versions of the same thing. We can examine the effect of each predictor on the response and hold all the other variables fixed. So this will allow us to do inference. So that means checking on the relationship between the variables rather than just making a prediction. So that's all to the good. The smoothness can be summarized via degrees of freedom, so that gives us a better interpretability. And the main limitation, of course, is that it's additive. So that's not really a terrible limitation, though. The reason it's not a terrible limitation is because we can still, with additive, we can still include interaction functions. So it's not, and we can definitely do things like local regression or two-dimensional splines within general additive models. So it's certainly more generalizable than anything we've seen so far, but it's not as generalizable as the things that we're going to see in the next chapter. So that's pretty much it for general additive models. In the next video, I'll go on to the lab on nonlinear modeling. Thanks for your attention.